Gravity does not exist. Not as a force, not as something pulling you down. For 3 centuries we have been teaching a lie. Isaac Newton gave us equations that worked, predictions that held, a framework that launched rockets and landed rovers. But he never explained what gravity actually was. Then in 1915, Albert Einstein shattered everything. He proved gravity is not a force at all. It is the shape of space and time themselves, warped by mass, bent into curves we cannot see but cannot escape. You're not being pulled toward Earth. You're standing still in curved space-time while the ground accelerates upward into you at 9.8 meters per second squared. That pressure, that weight you feel right now, is not gravity, it is resistance. You're being held off the natural path through the universe, and that path is what we mistook for falling. This is not philosophy, this is physics. If you are ready to see the truth that rewrites reality, hit that like button and subscribe. Prepare yourselves, we begin. For 300 years, humanity believed in a ghost. Isaac Newton published his law of universal gravitation in 1687, and it changed civilization. He proposed that every object with mass attracts every other object with mass. The force depends on their masses and the distance between them. Double the distance, the force drops to 1/4. Simple, elegant, undeniably accurate. His equations predicted planetary orbits with astonishing precision. They explained why apples fall and why moons orbit planets. They allowed astronomers to discover Neptune before anyone saw it, simply by calculating where an unseen mass must be tugging on Uranus. Newton's gravity worked perfectly for nearly everything humanity wanted to accomplish. But Newton himself knew something was wrong. He could describe how gravity behaved mathematically, but he could not explain what it actually was. How does the Sun reach across 93 million miles of empty space to hold Earth in orbit? What is the mechanism? Newton admitted he had no answer. He wrote that he would not feign hypotheses about the cause. The math worked, that was enough. Except it was not enough. The ghost remained, an invisible force, acting instantaneously across infinite distance, with no medium, no explanation, no physical reality beyond the numbers. The cracks began to show in the 19th century. Astronomers measuring Mercury's orbit found something strange. The planet's elliptical path rotates slowly over time, a phenomenon called precession. Most of the precession could be explained by gravitational tugs from other planets, but there was a tiny discrepancy. Mercury's orbit precessed an extra 43 arcseconds per century, more than Newton's equations predicted. 43 arcseconds is almost nothing. It is roughly 1/100th of a degree per century. But it was real, measurable, and unexplainable. Scientists proposed wild solutions. Maybe there was another planet closer to the Sun, a hidden world called Vulcan tugging on Mercury. Astronomers searched for decades. Vulcan did not exist. Then came Albert Einstein. In 1915, after nearly a decade of obsessive work, Einstein published his theory of general relativity. It was not an incremental improvement on Newton. It was a complete reconceptualization of reality itself. Einstein proposed that gravity is not a force. There is no invisible tug between masses. Instead, mass and energy warp the fabric of spacetime, and objects move along the curves created by that warping. Imagine spacetime as a stretched rubber sheet. Place a heavy ball on the sheet, and it creates a depression. Roll a smaller ball nearby, and it curves toward the depression, not because the heavy ball is pulling it, but because the sheet itself is curved. The smaller ball is following the straightest possible path through curved space. That path looks like an orbit to us, but from the ball's perspective it is moving in a straight line. This is gravity, not a force, geometry. Einstein's equations predicted Mercury's orbit perfectly. The extra 43 arcseconds per century appeared naturally in the math, explained by the way the Sun's mass warps spacetime near its surface. No hidden planet needed, no fudge factors, just geometry. The prediction was so precise, so perfectly aligned with observation, that Einstein later said his heart palpitated when he realized his equations worked. He knew he had touched something true about the universe, but the implications were terrifying. If gravity is not a force, then everything we feel as weight, as heaviness, as the pull of the Earth is something else entirely. You're not being pulled down right now. The ground is accelerating upward into you. You're trying to follow a natural path through curved space-time, a path we call free fall, and the surface of the Earth is blocking that path. The pressure you feel against your feet, against your chair, is not gravity. It is the electromagnetic forces in the atoms of the ground pushing against the atoms in your body, preventing you from following the curve. When you jump, you're not fighting gravity. You're briefly returning to your natural state, weightless, following the geodesic through space-time that mass and energy have carved. Then the ground rushes up to meet you again, and the acceleration resumes. Newton's ghost was banished. But what replaced it was far stranger than anyone imagined. The universe is not made of objects moving through empty space under the influence of forces. The universe is a four-dimensional fabric that bends, twists, and curves in response to the presence of matter and energy. We are not standing still. We are perpetually accelerating through a geometry we cannot see, held in place by a planet that will not let us fall. Therefore, the question becomes unavoidable. If space-time is a fabric that can be bent, what happens when you bend it too much? What lies at the extremes of curvature, where geometry itself begins to break? Space-time is not empty. This is the first thing you must understand to grasp what Einstein discovered. For most of human history, we imagined space as a void, a stage where objects move and interact. Time was something separate, a universal clock ticking forward at the same rate everywhere. Einstein proved both ideas wrong. Space and time are not separate. They are woven together into a single four-dimensional structure called space-time. And that structure is not passive. It is dynamic, flexible, and responsive to the presence of mass and energy. Think of space-time as a fabric, but not a metaphor. It is as real as the ground beneath your feet, though you cannot touch it or see it directly. This fabric has geometry. It can be flat, like a perfectly smooth sheet stretched tight, or it can be curved, warped by the presence of matter. When you place mass into space-time, the fabric bends around it. The more massive the object, the deeper the bend. The Sun creates a deep depression in space-time. Earth creates a smaller one. You create a depression so tiny it is almost unmeasurable, but it exists. Every atom, every particle with mass or energy contributes to the shape of space-time. The trampoline analogy helps visualize this, but it is imperfect. Imagine a flat trampoline stretched tight. Place a bowling ball in the center. The surface sags, creating a bowl-shaped depression. Now roll a marble near the edge. The marble does not travel in a straight line across the flat surface. It curves inward, spiraling toward the bowling ball. Not because the bowling ball is pulling it. The marble is simply following the shape of the curved surface. It is moving in the straightest possible path given the geometry it is traveling through. This is what planets do. Earth orbits the Sun because the Sun has warped space-time into a curve, and Earth is following that curve. But the trampoline analogy breaks down because it uses gravity to explain gravity. The bowling ball sags the trampoline downward because Earth's gravity pulls it. In real space-time, there is no down. The curvature is intrinsic to the fabric itself. Space-time curves in dimensions we cannot visualize directly because we are three-dimensional beings trying to picture four-dimensional geometry. The math describes it perfectly. Our brains cannot render it. We are stuck using shadows and analogies. Here is what makes space-time truly alien. You're moving through it right now at an enormous speed. Not just through space as Earth orbits the Sun and the Sun orbits the galactic center. You're moving through time. Every second you travel 1 second into the future. That sounds trivial, but it is not. In Einstein's framework, motion through space-time is constant. You're always moving at the speed of light through the combined dimensions of space and time. When you sit still in space, all your motion is through time. When you move through space, some of your motion shifts from the time dimension into spatial dimensions. This is why time slows down for objects moving at high speed. They're using up their motion through space-time by traveling through space, leaving less motion available for traveling through time. Gravity affects this motion. When space-time is curved, your path through it changes. Imagine walking across a field. If the ground is flat, you can walk in a straight line. If the ground has hills and valleys, your path curves even if you're trying to walk straight. You go uphill, downhill, around obstacles. Your trajectory through the landscape is determined by the shape of the terrain. Space-time works the same way. Mass creates hills and valleys in the four-dimensional terrain. Objects moving through that terrain follow paths determined by the curvature. You're standing on Earth right now, and Earth's mass has created a valley in space-time beneath you. The natural path through that valley is to fall toward the center of the Earth. That path is called a geodesic, the straightest possible line through curved space. But you're not following that geodesic. The ground is in the way. The atoms in the floor or the soil or the rock beneath your feet are pushing upward against you with electromagnetic force. That force is accelerating you upward, constantly. You do not feel like you're accelerating because you have no reference frame. But if you were in a windowless rocket in deep space accelerating, you would feel exactly the same sensation. Weight, pressure against your feet, the illusion of standing still. This is Einstein's equivalence principle, and it is the foundation of general relativity. You cannot tell the difference between gravity and acceleration. They are identical, not similar, identical. An observer in a closed room cannot perform any experiment that distinguishes between sitting on Earth's surface and accelerating through empty space. Both produce the same effects. Light bends the same way. Clocks tick at the same rate. Objects fall at the same speed. Therefore, gravity is not a force pulling you down. Gravity is the curvature of space-time, and what you feel as weight is the resistance of matter preventing you from following that curvature. The implications are staggering. When you drop a ball, the ball is not falling. The ball is trying to follow its natural geodesic through curved space-time. From the ball's perspective, it is weightless, unaccelerated, moving freely. You are the one being accelerated, held in place by the ground pushing up into you. The ball is in its natural state. You are not. This inverts everything we thought we understood about falling. Falling is not motion caused by a force. Falling is the absence of force. It is the natural, unaccelerated state of any object in curved space-time. But if space-time can curve gently around planets and stars, what happens when the curvature becomes extreme? What happens when mass compresses so tightly that the fabric of space-time bends not into a gentle valley, but into a pit so deep that nothing can climb out? What happens when geometry itself becomes a trap? Albert Einstein discovered the equivalence principle in 1907, 8 years before he completed general relativity. He called it the happiest thought of his life. He was sitting in his office at the patent office in Bern, Switzerland, when the idea struck him. If a person falls freely, they do not feel their own weight. A person in free fall is weightless. Einstein realized this was not just a curiosity. It was a fundamental clue about the nature of gravity itself. If you cannot feel gravity when you are falling, then gravity cannot be a force in the traditional sense. Forces act on objects. You feel forces. But you do not feel gravity when you fall. You feel nothing. You are weightless. Imagine you're standing in an elevator. The cable snaps. You and the elevator plummet toward the ground. Inside the elevator, you float. Your feet lift off the floor. If you release your phone, it hangs in the air beside you, motionless relative to you. You're both falling at the same rate, accelerating downward. But from your perspective inside the elevator, there is no acceleration. There is no up or down. You're weightless, drifting, as if you were floating in deep space far from any planet or star. You cannot tell you are falling unless you look outside. Now imagine a different scenario. You're in a windowless elevator in deep space, far from any massive object. There is no gravity. A rocket engine beneath the elevator fires, accelerating the elevator. Inside the elevator, your feet press against falls to the floor. You feel weight. You feel exactly the same sensation as standing on Earth's surface. Einstein realized these two situations are identical. You cannot distinguish between them with any experiment performed inside the elevator. Drop objects, shine light, measure time. Everything behaves the same way in both scenarios. Gravity and acceleration are equivalent. This equivalence is not approximate, it is exact. The laws of physics in a gravitational field are identical to the laws of physics in an accelerating reference frame. This means gravity cannot be a force acting on you, because forces do not vanish when you change reference frames. If gravity were a force pulling you toward Earth, you would still feel it when falling. But you do not. Therefore, gravity is not acting on you at all. What you experience as gravity is actually the effect of living in curved space-time and being prevented from following your natural path through that curvature. The terror of this realization is subtle but profound. You're not standing still. You never have been. Right now, as you read this, you are. The ground beneath you is pushing up into you with enormous force, accelerating every atom in your body continuously. You do not notice because you have no reference frame for comparison. but the acceleration is real. Your body is under constant stress. The atoms in your bones, your muscles, your organs are being compressed by the upward acceleration of the surface. That compression is what you feel as weight. When astronauts orbit Earth in the International Space Station, they are weightless. Not because there is no gravity at that altitude. Earth's gravitational field at the station's orbit is still about 90% as strong as it is on the surface. The astronauts are weightless because they are in free fall. They are following their natural geodesic through space-time, curving around Earth in an elliptical path. Nothing is pushing on them, no force is accelerating them. They are moving freely through curved space-time and therefore they feel nothing. They float, drift, tumble. This is the natural state of all objects, weightlessness, free motion along geodesics. You're not in that natural state. You're being held off your geodesic by. Those forces are immensely strong. The electrons in the atoms of your feet repel the electrons in the atoms of the floor. That repulsion prevents you from passing through the floor and following your geodesic toward Earth's center. The repulsion accelerates you upward continuously. The sensation of weight is the sensation of that upward acceleration pressing your body against itself. Einstein's equivalence principle leads to predictions that sound impossible but are true. Light should bend in a gravitational field. Here is why. Imagine you're in that windowless elevator in deep space, accelerating upward. A beam of light enters through a hole in one wall, traveling horizontally. From your perspective inside the accelerating elevator, the light curves downward. Not because anything is acting on the light travels in a straight line through space. But the elevator is accelerating upward while the light crosses it, so the light appears to curve. By the equivalence principle, if light curves in an accelerating elevator, it must also curve in a gravitational field. Therefore, gravity bends light. This prediction was tested in 1919 during a solar eclipse. Arthur Eddington led expeditions to observe stars near the sun's edge during totality. The sun's gravity should bend the light from those stars, making them appear slightly displaced from their true positions. Eddington's measurements confirmed Einstein's prediction. The stars shifted by the amount general relativity predicted. The result made Einstein world famous overnight. Newspapers proclaimed that space was curved, that Newton was overthrown, that reality itself had been rewritten. But the equivalence principle implies something darker. If you're constantly accelerating upward, what happens if that acceleration stops? What happens if the ground suddenly vanishes beneath you? You do not fall. You return to your natural state. You become weightless, following your geodesic freely. The sensation of falling is not the sensation of acceleration. It is the sensation of returning to rest in the truest sense. You stop accelerating. You stop being pushed. You simply move along the curve carved into space-time by Earth's mass. This means every step you take, every moment you stand, you are fighting your natural state. You are being held in place by forces that resist the shape of space-time itself. And space-time does not care. It will curve around you, beneath you, through you. If the matter holding you up fails, if the structure collapses, you will fall. Not because a force grabs you, because nothing is pushing you anymore. You will return to the path you were always meant to follow, the geodesic carved through four-dimensional space-time by the mass of the planet beneath you. But Earth's curvature of space-time is gentle. The geodesics near Earth are gradual slopes, easy to resist with solid matter. What happens when space-time curves so violently that the geodesics do not slope? What happens when every possible path, every geodesic, every trajectory through space-time points in one direction and one direction only? What happens when the curvature becomes so extreme that even light cannot escape? A geodesic is the shortest path between 2 points in curved space. On a flat surface, the shortest path is a straight line. On a sphere, the shortest path is a great circle, the kind of arc airplanes follow when flying long distances over Earth. The path curves not because the airplane is turning, but because the surface itself is curved. The airplane is following the straightest possible route across a curved geometry. This is a geodesic. In space-time, geodesics are the paths objects follow when no forces act on them. They are the natural trajectories through four-dimensional geometry. Every object follows a geodesic unless something intervenes. A planet orbits a star along a geodesic carved by the star's mass-warping space-time. A photon of light travels along a geodesic, curving near massive objects because space-time itself is curved. You, standing on Earth, are not on a geodesic. The ground is pushing you off your natural path, forcing you into a trajectory that does not follow the curvature. This is why you feel weight. You're being accelerated away from your geodesic by electromagnetic forces in matter. When you jump, you briefly return to a geodesic. For the fraction of a second you are airborne, you are weightless. You're in free fall following the curve of spacetime without interference. Then the ground interrupts again, slamming into you, accelerating you back off the geodesic. The impact is the ground exerting force on you, pushing you upward, preventing you from continuing along your natural path. If the ground were not there, you would fall toward Earth's center, accelerating not because a force is pulling you, but because the geodesic through Earth's curved spacetime points inward. Earth's geodesics are gentle. The curvature is mild enough that solid matter can easily resist it. Rock, metal, concrete, these materials push back against spacetime's curvature with electromagnetic forces strong enough to hold structures in place. The ground does not collapse into Earth's center because the atoms in rock repel each other with immense force. That repulsion balances the curvature. The structure holds. But not all geodesics are gentle. The Sun curves spacetime far more than Earth. The Sun's mass is 330,000 times Earth's mass, and it compresses that mass into a sphere only 109 times Earth's diameter. The result is a much deeper distortion of spacetime. Near the Sun's surface, geodesics curve sharply inward. If you could stand on the Sun's surface, which you cannot because it is a ball of plasma at 5,500 degrees Celsius, you would feel a gravitational acceleration 28 times stronger than on Earth. Your geodesic would plunge toward the Sun's core at 274 meters per second squared. The only reason the Sun does not collapse entirely is that the nuclear fusion in its core generates outward pressure. That pressure resists the curvature, holding the Sun in equilibrium. The inward pull of curved spacetime balances the outward push of fusion energy. For now. When the Sun exhausts its nuclear fuel in about 5 billion years, that balance will fail. Fusion will stop. The outward pressure will vanish. The geodesics will win. The Sun's core will collapse, compressing under its own curvature until electron degeneracy pressure stops it. Electrons cannot occupy the same quantum state, and when compressed tightly enough, they resist further compression with a force that does not depend on temperature. The Sun will become a white dwarf, a sphere roughly the size of Earth, but with half the Sun's original mass. The geodesics around a white dwarf are steep. The curvature is extreme, but it is still resistible. Stars more massive than the Sun face a worse fate. When a star 8 times the Sun's mass or larger exhausts its fuel, electron degeneracy pressure is not enough. The collapse continues. Electrons are forced into protons, creating neutrons. The core becomes a neutron star, a sphere perhaps 20 kilometers across containing more mass than the Sun. Neutrons resist compression through neutron degeneracy pressure, a quantum effect even stronger than the electron degeneracy. The geodesics near a neutron star are ferociously steep. Spacetime curvature near the surface is so extreme that falling objects accelerate at billions of meters per second squared. Time itself slows dramatically. A clock on a neutron star's surface ticks 30% slower than a clock far from any mass. Yet even this curvature can be resisted. Neutron degeneracy pressure holds the star against collapse. The structure survives, but there is a limit. If a collapsing stellar core exceeds roughly 3 solar masses, no known force can stop it. Neutron degeneracy pressure fails. The geodesics become so steep, the curvature so extreme, that matter itself cannot resist. The collapse continues. The core compresses past the neutron star state, past any configuration where particles can maintain separation, past the point where spacetime curvature can be balanced by any physical pressure. The geodesics spiral inward without limit. What forms is not an object. It is a region of spacetime so warped that all geodesics point one direction, inward, always inward. Nothing can follow an outward geodesic. Not matter, not light, not information. This is a black hole. The name is misleading. A black hole is not a hole in space. It is not a tunnel or a portal. It is a region where spacetime curvature has become so extreme that the geometry itself traps everything inside. The boundary of this region is called the event horizon. It is not a physical surface. There is nothing there to touch. It is simply the mathematical boundary where geodesics change character. Outside the horizon, geodesics can point outward. You can escape. You can climb away from the curvature if you accelerate hard enough. Inside the horizon, Every geodesic points inward toward the center. There are no outward paths. Not even light can follow an outward geodesic because no outward geodesics exist. Imagine standing just outside the event horizon of a black hole. You fire your rocket engines at full power, trying to hover in place. The geodesics around you curve sharply inward. You're accelerating upward, away from the black hole at an enormous rate. But the curvature is so steep that staying in place requires accelerating at nearly the speed of light. Your engines strain, your fuel burns, you hold position barely. Now imagine crossing the horizon. The moment you pass that boundary, the geometry changes. Every direction you look, every direction you could possibly travel, leads toward the center. Up is toward the center, down is toward the center, left and right are toward the center, forward in time is toward the center. You cannot avoid moving inward any more than you can avoid moving forward in time. The singularity at the center is not a place you will reach. It is a moment in your future that you cannot prevent. This is the terror of geodesics in extreme curvature. Near Earth, geodesics curve gently, and matter resists them easily. Near a neutron star, geodesics curve violently, but matter can still resist. Inside a black hole's event horizon, resistance becomes meaningless. The geodesics do not curve toward the center. They are the center. Spacetime itself has folded into a geometry where all paths lead to annihilation. You cannot fight geometry. You cannot push against the shape of spacetime. You can only follow the path carved into the fabric of reality, and inside a black hole, that path ends in destruction. But the event horizon is just the beginning. What lies at the center, where all geodesics terminate, is something physics cannot describe. What happens when curvature becomes infinite? Black holes are not objects that pull. This is the most common misconception. People imagine a black hole as a cosmic vacuum cleaner, sucking in everything nearby. That is wrong. A black hole does not pull any more than the sun pulls Earth. If the sun were replaced with a black hole of the same mass, Earth's orbit would not change. The geodesics carved by the sun's mass would remain identical. Earth would continue orbiting exactly as it does now, following the same path through spacetime. The only difference would be the absence of sunlight. Black holes do not exert some special attractive force. They simply curve spacetime, just like any other mass. What makes them unique is the extremity of that curvature. The event horizon is where that extremity becomes absolute. Outside the horizon, you can escape if you accelerate hard enough. A rocket with sufficient thrust can fire its engines and climb away from the black hole, following an outward geodesic. Light emitted outward escapes. Information can leave. The black hole's gravity is strong, but it is not fundamentally different from the gravity near any massive object. The geodesics curve steeply, but outward paths still exist. Cross the horizon, and that changes. The horizon is the surface where the escape velocity equals the speed of light. At that boundary, even a photon travelling straight outward at maximum speed cannot escape. It cannot climb out of the curvature. Its geodesic bends back inward. Here is what that means. The event horizon is not a barrier in space. It is a point of no return in spacetime geometry. Imagine spacetime as a flowing river. Far from the black hole, the current is gentle. You can swim against it. You can move upstream, downstream, or stay in place. Closer to the black hole, the current strengthens. Swimming upstream becomes harder. You must exert more effort to hold position. At the event horizon, the current reaches the speed of light. Even swimming at maximum speed, you cannot move upstream. You're dragged inexorably forward. Cross that line, and upstream ceases to exist as a direction. Every direction is downstream. Every path leads toward the waterfall ahead. The waterfall is the singularity. At the center of every black hole, general relativity predicts a point where spacetime curvature becomes infinite. Density becomes infinite. The volume occupied by the collapsed mass shrinks to zero. This is the singularity, and it is where the equations break. Infinity is not a physical value. It is a signal that the theory has reached its limit. General relativity describes spacetime curvature with exquisite precision everywhere except at singularities. There, the math produces infinities, and infinities mean the theory cannot tell you what happens next. Physics dies at the singularity, but you do not need to reach the singularity to be destroyed. Inside the event horizon, tidal forces become lethal long before you approach the center. Tidal forces arise because gravity is not uniform. Your feet, Closer to the black hole, follow a steeper geodesic than your head. The difference in curvature stretches you. Near Earth, tidal forces are negligible. The difference in gravitational acceleration between your head and feet is unmeasurable. Near a black hole, that difference becomes extreme. For a stellar mass black hole, perhaps 10 times the Sun's mass, tidal forces at the event horizon are strong enough to tear a human body apart. Your feet accelerate inward faster than your head. The difference rips you into pieces, stretching you vertically while compressing you horizontally. Astrophysicists call this spaghettification. Your body elongates into a thin strand of atoms, pulled inexorably toward the singularity. Supermassive black holes, millions or billions of times the Sun's mass, have much larger event horizons. The tidal forces at the horizon are weaker because the curvature is more gradual. You could cross the event horizon of a supermassive black hole and survive, at least initially. You would not feel anything unusual at the moment of crossing. There is no physical marker, no barrier, no sensation. You would simply pass through, continuing along your geodesic. Only later, as you fell deeper and the tidal forces grew, would destruction come. But by then, escape is impossible. You crossed the horizon, your future is determined, you will reach the singularity. It is as inevitable as tomorrow. From an outside perspective, you never cross the horizon. This is one of the strangest predictions of general relativity. Time dilation near a black hole becomes extreme. As you approach the horizon, time for you slows relative to an observer far away. To that distant observer, you appear to slow down, asymptotically approaching the horizon but never quite reaching it. Your image reddens as the light from your body stretches to longer wavelengths. Eventually you fade from view, your light redshifted into invisibility. The observer sees you frozen at the horizon forever, but from your perspective, you cross in finite time. You fall through the horizon and continue toward the singularity. Both perspectives are correct. Time itself fractures at the event horizon, splitting into irreconcilable reference frames. Inside the horizon, space-time does something even stranger. The radial direction, the direction toward the singularity, becomes time-like. Outside the horizon, moving inward or outward is a choice. You can move toward or away from the black hole by accelerating. Inside, moving toward the singularity is not a choice. It is the passage of time. Just as you cannot stop moving forward in time outside the black hole, you cannot stop moving toward the singularity inside. The singularity is not a place in space. It is a moment in time. It is in your future, unavoidable, approaching as surely as the next second. You will reach it. You will be destroyed by it, and there is nothing you can do to prevent it. What happens at the singularity? No one knows. General relativity predicts infinite curvature, infinite density, infinite tidal forces, but infinity is not physical. It is a placeholder for ignorance. The theory breaks down. Some physicists believe quantum effects become important at the singularity, preventing true infinite compression. Perhaps spacetime itself becomes discrete, grainy at the smallest scales, and the singularity spreads out into a quantum foam. Perhaps the collapse stops at some tiny but finite size, or perhaps singularities are real, and the universe contains points where the fabric of spacetime is torn, where the laws of physics cease to apply, where reality itself ends. Black holes are not the only places where singularities appear. General relativity predicts another singularity in our past, the Big Bang. If you run the equations backward, tracing the expansion of the universe in reverse, everything converges to a single point roughly 13.8 billion years ago. Infinite density, infinite temperature, infinite curvature. The same mathematical breakdown occurs. The universe itself emerged from a singularity, a moment when the equations fail and physics cannot describe what happened. We do not know what the Big Bang was. We know it happened. We see the evidence in the cosmic microwave background, in the expansion of space, in the abundance of light elements. But the initial moment, the singularity itself, remains beyond our understanding. Singularities represent the edge of knowledge. They are where general relativity admits defeat, where the smooth geometry of space-time shatters into mathematical chaos. Einstein's theory describes the universe with stunning accuracy everywhere except these points. And that failure is terrifying because it means we do not understand reality at its most extreme. We do not know what happens inside black holes. We do not know what happened at the beginning of the universe. We have equations that work almost everywhere, but they fail precisely where we most need them. The geodesics lead to singularities. Physics cannot follow, but spacetime does more than curve. It can ripple, and those ripples carry information about the most violent events in the cosmos. Spacetime is not rigid, it flexes, it vibrates. When massive objects accelerate violently, they send ripples through the fabric of spacetime itself, distortions that propagate outward at the speed of light. These ripples are called gravitational waves. Einstein predicted their existence in 1916, 1 year after publishing general relativity. The equations showed that accelerating masses should radiate energy in the form of spacetime curvature fluctuations, just as accelerating electric charges radiate electromagnetic waves. But Einstein doubted they could ever be detected. The effect is extraordinarily weak. Spacetime is stiff. It resists distortion. Only the most catastrophic cosmic events generate waves strong enough to measure. For nearly a century, gravitational waves remained theoretical. Physicists searched for indirect evidence. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other at tremendous speed. The orbit was decaying. The stars were spiraling closer together, losing energy. General relativity predicted this energy loss. The orbiting neutron stars should radiate gravitational waves, carrying orbital energy away into space. The rate of decay matched Einstein's predictions exactly. Hulse and Taylor won the Nobel Prize in 1993 for confirming gravitational waves exist, even though no one had detected them directly. Direct detection came on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, recorded a signal that lasted 1/5 of a second. Two detectors, one in Louisiana and one in Washington state, separated by 3,000 kilometers, detected the same signal within milliseconds of each other. The waveform was unmistakable, a chirp, a rising frequency and amplitude that matched the predicted signature of two black holes spiraling together and merging. The black holes were 36 and 29 times the Sun's mass. They orbited each other hundreds of times per second in the final moments before collision. When they merged, they released more energy in gravitational waves than all the stars in the observable universe combined were emitting in light at that instant. 3 solar masses of energy, converted entirely into spacetime ripples, radiated outward in a fraction of a second. The wave travelled through space for 1.3 billion years before reaching Earth. By the time it arrived, it had weakened enormously. The distortion it caused in spacetime was infinitesimal. LIGO detected a change in distance of 1/10,000th, the width of a proton. The detectors use laser beams travelling along 4-kilometre arms arranged in an L shape. When a gravitational wave passes, it stretches space in one direction and compresses it in the perpendicular direction. The laser beams detect this change through interference patterns. The precision required is almost unimaginable. LIGO can measure changes in arm length smaller than the nucleus of an atom across a distance of 4 kilometres. It is the most sensitive measuring instrument ever built. The detection confirmed Einstein was right. Gravitational waves are real. Space-time can vibrate. But the discovery revealed something more profound. Gravitational waves provide a new way to observe the universe. Light tells us about electromagnetic processes. Stars, galaxies, gas and dust emit light because they are hot or energized. But gravitational waves tell us about space-time itself. They are emitted by mass in motion, by the acceleration of massive objects. Colliding black holes do not emit light. They are dark, but they scream in gravitational waves. Neutron star collisions, supernovae, even the Big Bang itself should have produced gravitational waves. We can now listen to these events directly, observing the universe through the vibrations of space-time rather than through light. Since 2015, LIGO and its partner detector Virgo in Italy have detected dozens of gravitational wave events. Most are black hole mergers, some are neutron star mergers. In August 2017, LIGO and Virgo detected 2 neutron stars colliding. Telescopes around the world turned toward the source and saw a kilonova, a brilliant explosion powered by the radioactive decay of heavy elements formed in the collision. This was the first time a cosmic event was observed in both gravitational waves and light. The combination revealed details impossible to learn from either signal alone. The collision synthesized gold, platinum, uranium and other heavy elements, scattering them into space. Most of the gold on Earth likely came from neutron star collisions billions of years ago. Gravitational waves let us watch that process happening in real time. But gravitational waves also reveal the nature of spacetime itself. When a wave passes through you, spacetime stretches and compresses. You stretch and compress with it. The effect is far too small to feel. LIGO detects changes of 10 to the minus 18 meters. Your body is not rigid enough to notice distortions that tiny. But the distortion is real. Spacetime is not an abstract mathematical concept. It is a physical thing that can be bent, rippled, vibrated. Gravitational waves prove spacetime is as real as matter and energy. The waves also carry information encoded in their frequency and amplitude. The chirp detected by LIGO told physicists the masses of the colliding black holes, how fast they were spinning, how far away the collision occurred, and even the orientation of the orbital plane. All this from the waveform is a fingerprint of the event, shaped by the geodesics near the merging black holes. As the black holes spiral inward, they orbit faster and faster. The geodesics they follow become tighter. The orbital frequency increases. The gravitational waves they emit increase in frequency and amplitude, producing the characteristic chirp. When the horizons touch and the black holes merge, the waveform cuts off abruptly. A single, larger black hole remains, its event horizon quivering as it settles into equilibrium. That quivering, called ringdown, also emits gravitational waves, a decaying tone that reveals the mass and spin of the final black hole. The detection of gravitational waves opened a new era in astronomy. Future detectors will be even more sensitive. The Laser Interferometer Space Antenna, or LISA, will launch in the 2030s. It will consist of 3 spacecraft separated by 2.5 million kilometers, forming a triangle in space. LISA will detect lower frequency gravitational waves from supermassive black hole mergers, events involving. These mergers happen when galaxies collide and their central black holes spiral together over millions of years. LISA will hear them years before they merge, tracking the spiral in exquisite detail. Gravitational waves also offer a way to test general relativity in extreme conditions. Near colliding black holes, spacetime curvature is so intense that Einstein's equations are pushed to their limits. If general relativity is wrong or incomplete, deviations should appear in the gravitational waveforms. So far, every detected signal matches predictions perfectly. General relativity holds even in the most violent environments we can observe, but the theory predicts its own failure at singularities. Gravitational waves cannot tell us what happens there. They carry information only from outside the event horizon. What lies inside remains hidden. Spacetime ripples, but it does not tear. Or does it? Some physicists speculate that under extreme conditions, spacetime itself might fracture, creating discontinuities or defects in the fabric. Cosmic strings, hypothetical one-dimensional defects left over from the early universe, would generate gravitational waves if they exist. None have been detected. If spacetime can ripple, perhaps it can break. Perhaps the fabric is not infinitely flexible. Perhaps there is a limit to how much it can be distorted before something fundamental fails. Einstein introduced one more element into his equations, something he later regretted. And that element has become the most mysterious component of the universe. In 1917, Albert Einstein faced a problem. His equations of general relativity, published 2 years earlier, predicted that the universe should be dynamic, either expanding or contracting. Spacetime filled with matter cannot remain static. The curvature created by mass causes space itself to evolve over time. But in 1917, everyone believed the universe was eternal and unchanging. Galaxies had not yet been discovered. Astronomers thought the Milky Way was the entire universe, a static island of stars surrounded by infinite empty space. Einstein trusted the consensus. If the universe was static, his equations must be wrong, so he modified them. He added a term called the cosmological constant, represented by the Greek letter lambda. This term represents a property of spacetime itself, an intrinsic energy density that does not dilute as space expands. It acts as a repulsive pressure, counteracting the attractive curvature caused by matter. Einstein tuned the cosmological constant precisely to balance gravity, creating a static universe in his equations. The modification worked mathematically. The universe could remain frozen, unchanging, eternal. Einstein published the revised equations and moved on. 12 years later, Edwin Hubble discovered that the universe is not static. By observing distant galaxies, Hubble found they are all moving away from us. The farther away a galaxy is, the faster it recedes. Space itself is expanding, carrying galaxies apart. The universe had a beginning. It is dynamic, evolving, exactly as Einstein's original equations predicted. Einstein called the cosmological constant his greatest blunder. He had modified a perfectly good theory to fit wrong assumptions about reality. If he had trusted his equations, he could have predicted cosmic expansion before it was observed. But the story does not end there. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery. The universe's expansion is not slowing down. It is accelerating. Galaxies are moving apart faster now than they were billions of years ago. Something is driving space to expand at an increasing rate. That something has been named dark energy, and it behaves exactly like Einstein's cosmological constant. The blunder was not a blunder. The cosmological constant is real. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter, the invisible substance that holds galaxies together, accounts for 27%. Ordinary matter, everything made of atoms, stars, planets, gas, dust, and living things, is only 5%. The universe is dominated by components we do not understand. Dark energy is the most mysterious of all. We know it exists because we observe its effects. We do not know what it is. The simplest explanation is that dark energy is the cosmological constant, a fixed energy density built into the structure of spacetime itself. Every cubic meter of space contains a tiny amount of energy, roughly 6 times 10 to the minus 10 joules per cubic meter. This sounds negligible, but space is vast. Summed over the observable universe, the total dark energy is enormous, and because it is a property of space, not of matter or radiation, it does not dilute as space expands. When the universe doubles in size, the volume doubles and the total dark energy doubles. Matter and radiation dilute as space expands. Dark energy does not. Therefore, dark energy becomes more dominant over time. In the early universe, matter and radiation dominated. Gravity from matter slowed the expansion. For the first several billion years, the universe decelerated, expanding more slowly as time passed. Then, as space expanded and matter diluted, dark energy became relatively more important. About 6 billion years ago, dark energy began to dominate. The expansion stopped decelerating and started accelerating. This acceleration will continue indefinitely if dark energy remains constant. The universe will expand faster and faster, forever. The implications are disturbing. Dark energy is not just accelerating expansion, it is tearing the universe apart. Structures that are not gravitationally bound will eventually lose all contact. Galaxy clusters held together by their own gravity will survive, but clusters that are separating now will recede beyond each other's cosmic horizons. Light from one cluster will never reach the other. The universe will fragment into isolated islands, each surrounded by an expanding void that grows faster than light can cross it. Distant galaxies we see today will disappear from view as their light redshifts into invisibility. The night sky will darken. In the far future, observers in our galaxy will see only the local group of gravitationally bound galaxies. Everything else will be gone, hidden beyond an unreachable horizon. But we do not know if dark energy is truly constant. The cosmological constant is one possibility. Another is that dark energy is a dynamic field, something that changes over time. If dark energy strengthens, the acceleration will intensify. Eventually, even gravitationally bound structures could be torn apart. Galaxy clusters would dissolve, galaxies would fragment, solar systems would unbind. In the most extreme scenario, called the Big Rip, dark energy becomes so strong that it rips apart atoms themselves. The fabric of space-time expands so violently that electromagnetic forces cannot hold electrons to nuclei. Matter disintegrates into subatomic particles. Then those particles are torn apart. Space-time itself might fracture. This scenario is speculative, but it is consistent with some models of dark energy. Observations so far suggest dark energy is constant or nearly constant, but the uncertainties are large enough that a big rip cannot be ruled out. Alternatively, dark energy could weaken. If it decays or reverses sign, the universe's expansion could slow and eventually reverse. Space would begin contracting. Galaxies would collide. The cosmic microwave background radiation would blue shift, heating up. Eventually, everything would collapse back into a hot, dense state, a big crunch. The universe would end in fire, crushed by its own curvature. This seems less likely given current observations, but it is not impossible. The mystery of dark energy runs deeper than its future behavior. Why does it have the value it does? The observed energy density of dark energy is extraordinarily small by particle physics standards. Quantum field theory predicts that empty space should have an enormous energy density, roughly 10 to the 120 times larger than what we observe. This is called the cosmological constant problem, and it is one of the worst prediction failures in physics. The theoretical value is wrong by 120 orders of magnitude. Something cancels almost all of the vacuum energy, leaving only a tiny residual that we observe as dark energy. No one knows what causes this cancellation, or why the remaining value is so small yet non-zero. Another mystery is the coincidence problem. Dark energy and matter have comparable densities today. Dark energy is about twice as dense as matter, but their densities evolve differently. Matter density decreases as the universe expands. Dark energy density stays constant. In the early universe, matter dominated by a huge factor. In the far future, dark energy will dominate by a huge factor. The fact that we live in the brief era when their densities are similar seems suspicious. Why now? Is it coincidence, or does it indicate something deeper about the relationship between matter and dark energy? Some physicists propose that dark energy is not a property of spacetime but a new field, similar to the inflaton field thought to drive cosmic inflation in the first moments after the Big Bang. This field, called quintessence, could vary in space and time, creating a dynamical dark energy that evolves as the universe ages. Quintessence models can explain why dark energy became important recently, but they introduce new parameters and unknowns. No compelling evidence supports quintessence over the cosmological constant yet. Others suggest modifying general relativity itself. Perhaps gravity works differently on cosmological scales. Modified gravity theories can mimic the effects of dark energy without requiring a mysterious energy component. But these theories face challenges. They must reproduce all the successes of general relativity, including gravitational wave observations, while also explaining cosmic acceleration. Most modified gravity theories fail one test or another. Dark energy is Einstein's cosmological constant returned from the grave. He introduced it for the wrong reasons, discarded it, and now it dominates the universe. Its existence means space-time has intrinsic energy, a pressure that pushes space apart. The fabric of reality is not passive. It exerts force, it drives cosmic evolution, and we do not know why. We do not know what it is made of, whether it changes, or what determines its strength. We only know it is there, stretching space, accelerating expansion, shaping the ultimate fate of everything. Therefore, the question becomes inescapable. If space-time itself contains energy and pressure, what else is hidden in its structure? What other properties does space-time have that we have not yet discovered? General relativity describes gravity perfectly at every scale we can test. From millimeter precision experiments in laboratories to the orbits of planets, from the bending of starlight to the inspiral of colliding black holes, Einstein's equations work. They predict gravitational time dilation measured by atomic clocks on airplanes. They predict the precession of Mercury's orbit. They predict the exact waveform of gravitational waves from merging neutron stars. Every test confirms the theory. General relativity is one of the most successful scientific theories ever constructed. But it is incomplete. The problem reveals itself at the smallest scales. General relativity treats spacetime as a smooth, continuous fabric. Zoom in arbitrarily far, and the fabric remains smooth. There are no gaps, no graininess, no fundamental smallest unit. Space-time is infinitely divisible in Einstein's theory. But quantum mechanics tells a different story. At the smallest scales, everything becomes discrete. Energy comes in packets called quanta. Particles exist in probabilistic states. The smooth, deterministic world of classical physics dissolves into uncertainty and discreteness. Every force except gravity has a quantum description. Electromagnetism is mediated by photons. The strong nuclear force is mediated by gluons. The weak nuclear force is mediated by W and Z bosons. These forces are understood through quantum field theory, a framework that combines quantum mechanics with special relativity. The theories work spectacularly well, predicting phenomena with extraordinary precision. Gravity does not fit. No one has successfully combined general relativity with quantum mechanics. The two frameworks are fundamentally incompatible. General relativity requires smooth spacetime. Quantum mechanics requires discreteness and uncertainty. When physicists try to apply quantum mechanics to gravity, the equations break down. They produce infinities that cannot be removed. The theory becomes non-renormalizable, a technical term meaning the infinities cannot be absorbed into redefined constants. The math fails. We do not have a quantum theory of gravity. This failure matters because there are places where both quantum mechanics and general relativity should apply simultaneously. Inside black holes, near the singularity, spacetime curvature becomes extreme and the region becomes microscopic. Quantum effects cannot be ignored. At the Big Bang, the entire universe was compressed to subatomic size with infinite curvature. Quantum mechanics and gravity were both crucial. We cannot describe these situations with either theory alone. We need a unified framework, a theory of quantum gravity. We do not have one. The scale where quantum gravity becomes important is called the Planck scale. The Planck length is roughly 10 to the minus 35 meters, far smaller than an atom, smaller than a proton, smaller than anything we can probe experimentally. At this scale, quantum fluctuations in spacetime itself become significant. Spacetime may not be smooth. It may be a seething foam of quantum fluctuations, with virtual black holes forming and evaporating, wormholes appearing and vanishing, the fabric itself bubbling and churning. This is speculation. No one knows what spacetime looks like at the Planck scale, because we have no theory to describe it, and no experiments that can reach it. Several candidates for quantum gravity exist. String theory proposes that fundamental particles are not point-like but tiny vibrating strings. Different vibration modes correspond to different particles. Gravity emerges from a particular vibration mode, the graviton, a hypothetical particle that mediates gravitational force. String theory requires extra dimensions of space beyond the three we observe. These extra dimensions are compactified, curled up so small we cannot detect them. String theory is mathematically elegant and has produced deep insights into theoretical physics, but it makes few testable predictions. No experiment has confirmed strings exist. No one has observed extra dimensions. String theory remains unverified. Loop quantum gravity takes a different approach. It attempts to quantize spacetime itself, treating space and time as made of discrete loops. Spacetime is not continuous but granular, built from finite chunks called spin networks. In this framework, spacetime has a smallest possible unit. You cannot divide space or time beyond the Planck scale. Loop quantum gravity avoids some of the infinities that plague other approaches, but it struggles to reproduce general relativity at large scales. The theory is incomplete. Other approaches include causal set theory, which treats spacetime as a collection of discrete points with causal relationships. Asymptotic safety, which proposes that gravity becomes well-behaved at high energies in a way that makes quantum calculations work. Emergent gravity, which suggests spacetime and gravity are not fundamental, but arise from deeper quantum information. None of these theories are complete. None have been experimentally confirmed. We are groping in the dark. The lack of quantum gravity has profound consequences. We cannot understand what happens at the center of a black hole. General relativity predicts a singularity with infinite curvature, but infinities signal the theory's failure. Quantum gravity should resolve the singularity, replacing it with something finite. Perhaps the collapse stops at the Planck scale. Perhaps spacetime becomes a quantum superposition of different geometries. Perhaps the singularity is replaced by a bounce, a transition to another region of spacetime. We do not know. Without quantum gravity, the singularity remains a mystery. The same problem applies to the Big Bang. General relativity traces cosmic expansion backward to a singularity 13.8 billion years ago, a moment of infinite density and temperature. But the theory cannot describe that moment. Quantum effects must dominate when the universe was smaller than the Planck length. What happened then? Did time begin at the Big Bang, or did something exist before? Did the universe emerge from a quantum fluctuation, a random event in a pre-existing quantum vacuum? Or is the Big Bang a transition from a previous collapsing phase? These questions cannot be answered without quantum gravity. Hawking radiation offers a tantalizing clue. In 1974, Stephen Hawking used quantum field theory and curved spacetime to show that black holes are not completely black. Quantum fluctuations near the event horizon create particle-antiparticle pairs. Normally, these pairs annihilate immediately, but near a black hole, one particle can fall in while the other escapes. The escaping particle appears as radiation emitted by the black hole. The black hole loses mass in the process. Over immense timescales, far longer than the current age of the universe, even supermassive black holes will evaporate completely through Hawking radiation. This prediction is extraordinary. It means black holes have temperature. They emit thermal radiation like hot objects. The temperature is inversely proportional to mass. Stellar mass black holes have temperatures a millionth of a degree above absolute zero, far colder than the cosmic microwave background. They absorb more radiation than they emit. But as a black hole evaporates and loses mass, its temperature rises. The final moments of evaporation are explosive, releasing enormous energy as the black hole vanishes. Hawking radiation has never been observed. Black holes are too cold and evaporation too slow for current technology to detect. But the theoretical prediction is robust, arising naturally from combining quantum mechanics with curved spacetime. Hawking radiation creates a paradox: information. In quantum mechanics, information is never destroyed. The state of a system evolves deterministically according to quantum laws. If you know the initial state, you can predict the final state. But if a black hole evaporates completely, where does the information about the matter that fell in go? The radiation emitted is thermal, random, containing no information about what fell in. The information appears to be destroyed, violating quantum mechanics. This is the black hole information paradox, and it remains unsolved. Some physicists believe information is somehow encoded in the Hawking radiation, in subtle correlations we do not yet understand. Others propose information is stored on the event horizon, or leaks out through quantum effects we have not calculated. The paradox suggests our understanding of spacetime, quantum mechanics, or both is incomplete. The quest for quantum gravity is the quest to understand reality at its most fundamental level. Spacetime may not be the bedrock of existence. It may emerge from something deeper, something purely quantum. If so, space and time themselves are approximate concepts, valid at large scales but breaking down at the Planck scale. We may be living in an illusion, mistaking an emergent phenomenon for fundamental reality. This possibility is both exhilarating and terrifying. Exhilarating because it suggests a deeper layer of reality waiting to be discovered. Terrifying because it means everything we think we know about space, time, and gravity may be wrong in ways we cannot yet imagine. Einstein gave us general relativity, a geometric theory of gravity that describes the universe with breathtaking accuracy. But the theory contains the seeds of its own destruction. Singularities, infinities, breakdowns at the quantum scale. These are not minor flaws, they are fundamental limits. General relativity tells us it is not the final answer. Something deeper exists. We have not found it yet. Therefore, the question remains open, hanging over all of cosmology and fundamental physics. What is space-time really? And what replaces it when the fabric tears? Space-time might not be fundamental. This is the possibility that keeps physicists awake at night. For a century, we have treated space-time as the stage on which physics unfolds. Particles move through space-time. Fields permeate space-time. Forces act within space-time. But what if space-time itself is not elemental? What if it emerges from something deeper, something we have not yet identified? This idea, called emergent space-time, suggests that space and time are collective phenomena arising from more fundamental quantum degrees of freedom, much like temperature emerges from the motion of atoms or pressure emerges from molecular collisions. The evidence comes from surprising places. Black hole thermodynamics provides the clearest hint. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy. Entropy measures disorder, the number of ways a system can be arranged microscopically while looking the same macroscopically. For ordinary objects, entropy is proportional to volume. A larger box of gas has more entropy than a smaller box because there are more ways to arrange the molecules. But black hole entropy is proportional to surface area, specifically the area of the event horizon. This is bizarre. It suggests that the information content of a black hole is stored not in its volume but on its two-dimensional surface. This led to the holographic principle, one of the most radical ideas in theoretical physics. The principle states that all the information contained in a volume of space can be encoded on the boundary of that volume. The three-dimensional reality we experience might be a projection from information stored on a two-dimensional surface, like a hologram. If true, this means one dimension of space is redundant, an illusion created by the way information is organized. Space-time is not what it seems. String theory provides mathematical support for the holographic principle through something called the AD-CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence relates a gravitational theory in a curved spacetime to a quantum field theory without gravity living on the boundary of that spacetime. The gravitational theory includes an extra dimension. The boundary theory does not, yet they describe the same physics. This is holography made precise. Gravity and spacetime emerge from quantum entanglement in the boundary theory. Space is not fundamental. It is a consequence of how quantum information is organized. Entanglement is the key. Quantum entanglement links particles in ways that defy classical intuition. When two particles are entangled, measuring one instantly affects the other, regardless of the distance separating them. Einstein called this spooky action at a distance, and suspected it revealed a flaw in quantum mechanics. But experiments confirm entanglement is real. It is a fundamental feature of quantum systems. Recent work suggests that space-time itself might be woven from entanglement. The connectivity of space, the fact that distant points are connected by paths you can travel, might arise from entanglement between quantum degrees of freedom. Where entanglement is strong, space is connected. Where entanglement is weak or absent, space is disconnected. Space-time is the pattern of quantum correlations. This picture has profound implications. If space-time emerges from entanglement, then destroying entanglement destroys space-time. Inside a black hole, as you approach the singularity, quantum entanglement might break down. Space-time dissolves. The singularity is not a point where curvature becomes infinite. It is a region where space-time ceases to exist because the entanglement structure supporting it has collapsed. The equations of general relativity break down not because they encounter infinity, but because space-time itself ends. There is nothing left to describe. The Big Bang might be the same phenomenon in reverse. Before the Big Bang, there was no space-time because there was no entanglement structure to support it. The universe did not emerge from a singularity in pre-existing space. Space-time itself emerged, crystallizing from a quantum state that had no spatial or temporal extension. Time did not exist before the Big Bang. The question of what came before is meaningless, because before requires time, and time did not exist. The universe began not as a point in space, but as the beginning of space itself. This resolves some paradoxes, but creates new questions. What is the quantum state from which space-time emerges? What are the fundamental degrees of freedom? Are they strings, loops, quantum bits of information, or something else entirely? No one knows. The mathematics is extraordinarily difficult. Space-time emergence is not a fully developed theory. It is a collection of ideas, hints, and partial calculations suggesting a direction. The full theory of quantum gravity remains out of reach. One approach treats space-time as an error-correcting code. Quantum information can be encoded in ways that protect it from corruption. If some quantum bits are damaged, the information can be recovered from the remaining bits. Space-time might function similarly, with the geometry of space encoding quantum information redundantly. This would explain why space-time is smooth and continuous at large scales, despite being built from discrete quantum components. The redundancy averages out the quantum noise, producing the classical space-time we observe. This idea connects quantum gravity to quantum computing and information theory, fields that study how information is stored, processed, and protected. Another clue comes from cosmology. The universe's expansion might be driven not by dark energy as a substance, but by the quantum entanglement structure of space-time itself. As the universe expands, the entanglement between distant regions weakens. The weakening entanglement might appear as an effective repulsive pressure, mimicking dark energy. This is speculative, but it suggests that cosmic acceleration and quantum gravity are connected. Understanding one might illuminate the other. The possibility that space-time is not fundamental forces a rethinking of everything. If space and time emerge, then so does gravity. Gravity is not a force or a curvature in a fundamental fabric. Gravity is the name we give to the way emergent spacetime behaves when matter and energy are present. The geodesics objects follow are not paths through a pre-existing geometry. They are patterns in the entanglement structure. Mass does not curve spacetime. Mass changes the entanglement, and that change manifests as curvature. This is a complete inversion of how we think about gravity. It also means the constants of nature, the numbers that appear in our equations, might not be fundamental. The speed of light, the gravitational constant, Planck's constant, these might be emergent properties of the entanglement structure. In a different entanglement configuration, the constants could have different values. This opens the door to multiverse ideas where different regions of a larger reality have different physical laws because they have different entanglement structures. Our universe, with its specific constants and properties, is one possibility among many. The terror lies in the implications. If spacetime is not fundamental, then the ground beneath our feet, the air we breathe, the time we experience, all of it is an illusion. Not an illusion in the sense of being false, but an illusion in the sense of being a higher-level description that breaks down when examined closely. You're not really moving through space. You're a pattern in a quantum information structure, and the sensation of motion is how that pattern experiences its own evolution. The universe is not a place. It is a calculation, a flow of information, a self-organizing quantum system. You are not in the universe. You are part of the computation. This is where Einstein's terrifying truth reaches its conclusion. Gravity does not exist as a force. Space-time is not fundamental. Reality at the deepest level is something entirely alien to human intuition, built from principles we are only beginning to glimpse. We live in a cosmos that is stranger, more fluid, and more fragile than we imagined. The fabric of space-time can ripple, stretch, and tear. It can emerge and dissolve. It is not the eternal stage of existence, but a temporary structure, a pattern stabilized by quantum entanglement, destined to change as the universe evolves, and we are only beginning to see the cracks. The cracks are everywhere once you know where to look. General relativity works perfectly until it doesn't. Singularities are the most obvious cracks, points where the equations produce infinities and physics stops making predictions. But there are subtler failures. Dark energy is a crack. We observe cosmic acceleration, insert a term into Einstein's equations to match observations, but we have no idea why that term exists or what determines its value. Dark matter is another crack. Galaxies rotate too fast. Clusters hold together with more gravity than visible matter can provide. We infer invisible mass, call it dark matter, and move on. But we have not detected dark matter particles despite decades of searching. Perhaps they exist and we have not looked in the right place. Or perhaps gravity behaves differently than general relativity predicts on galactic scales, and the missing mass is an illusion created by our incomplete theory. The cosmological constant problem is a crack so enormous it threatens to swallow theoretical physics whole. Quantum field theory predicts that empty space seethes with virtual particles, fluctuations popping in and out of existence. These fluctuations contribute energy to the vacuum. When you calculate how much energy, the answer is the dark energy we observe. This is not a small error. It is the worst prediction in the history of physics. A tiny residue. No one knows what. No theory explains it. The cosmological constant problem is a crack between quantum mechanics and gravity, a chasm we cannot bridge. The measurement problem in quantum mechanics is another crack. Quantum systems exist in superpositions, multiple states simultaneously until measured. Measurement collapses the superposition into a single outcome. But what counts as a measurement? When does collapse happen? Quantum mechanics does not say. The theory describes probabilities beautifully, but says nothing about why one outcome occurs rather than another. Some physicists believe consciousness is required to collapse the wave function. Others believe collapse is an illusion, and all outcomes occur in parallel universes. Still others believe quantum mechanics is incomplete, and a deeper theory will explain collapse. No consensus exists. The measurement problem has persisted for a century with no resolution. These cracks suggest our theories are approximations, effective descriptions that work within certain limits, but fail when pushed too far. General relativity is an effective theory of gravity valid at low energies and weak curvature. Quantum field theory is an effective theory of particles and forces valid below the Planck scale. Neither theory is final. Both point beyond themselves to something deeper. We do not know what that something is. String theory was supposed to be the answer. In the 1980s and 90s, physicists hoped string theory would unify all forces, explain all particles, and provide a quantum theory of gravity. Early results were promising. String theory naturally includes gravity. The graviton emerges as a vibration mode of the string. The theory is mathematically consistent in ways previous attempts at quantum gravity were not. It avoids the infinities that plagued earlier approaches, but string theory has problems. It requires 10 or 11 dimensions, most of which must be hidden from observation. There are vast numbers of ways to curl up the extra dimensions, each giving different physics. This landscape of possibilities contains perhaps 10 to the 500 different vacuum states, each corresponding to a different universe with different physical laws. String theory does not predict which vacuum we inhabit. It does not predict the masses of particles, the strengths of forces, or the value of the cosmological constant. It explains nothing specific about our universe. After 4 decades of work, string theory has produced no testable predictions that distinguish it from other theories. It remains mathematically fascinating but empirically unverified. Loop quantum gravity has similar issues. It quantizes spacetime, eliminating singularities and infinities, but predicts that spacetime is granular at the Planck scale. But there is no way to test this prediction with current technology. The discreteness is far too small to observe. Loop quantum gravity also does not unify gravity with the other forces. It is a theory of quantum gravity alone, leaving the standard model of particle physics as a separate framework. A true theory of everything should unify all forces and explain why the universe has the particles and interactions it does. Loop quantum gravity does not do this. Other approaches face their own obstacles. Causal set theory treats spacetime as discrete points, but has difficulty reproducing smooth geometry at large scales. Asymptotic safety requires the gravitational coupling constant to behave in specific ways at high energy, which is not proven and may not be true. Emergent gravity ideas are compelling but incomplete, more philosophy than physics at this stage. Every approach to quantum gravity is either untestable, incomplete, or both. We are stuck. The crisis runs deeper than any single theory. We may be asking the wrong questions. For centuries, physics progressed by unifying disparate phenomena. Electricity and magnetism were unified into electromagnetism. Electromagnetism and the weak nuclear force were unified into the electroweak force. Perhaps gravity will someday unify with the other forces into a grand unified theory, or a theory of everything. But what if unification is not the right goal? What if gravity is fundamentally different from other forces because it is not a force at all, but an emergent property of spacetime, and spacetime itself is emergent? Then the quest to unify gravity with quantum field theory is misguided. You cannot unify something emergent with something fundamental. You must first understand what spacetime emerges from. This brings us to the edge of knowledge. The Planck scale is the limit of our theories and the limit of conceivable experiments. To probe distances as small as the Planck length, 10 to the minus 35 meters, you would need a particle accelerator the size of the galaxy. The energy required is 10 to the 19 giga-electron volts, a billion times higher than the Large Hadron Collider can reach. We will never build such an accelerator. We cannot directly observe quantum gravity effects. We must rely on indirect evidence, subtle clues from cosmology, black holes, and gravitational waves. Progress will be slow, it may take centuries, or we may never figure it out. Some physicists despair. They argue we have reached the limits of what humans can discover. The fundamental laws may be inaccessible, hidden behind energy scales we cannot reach, and mathematics we cannot solve. This is the nightmare scenario, that the universe's deepest secrets are forever beyond our grasp, not because we lack intelligence, but because the questions require experiments we cannot perform and calculations we cannot complete. We are insects trying to understand quantum field theory. The task is not just difficult, it may be impossible. Others remain optimistic. They point to history. Every time physicists declared they had discovered everything, new phenomena appeared. Classical mechanics seemed complete until quantum mechanics. Quantum mechanics seemed complete until quantum field theory. The standard model seemed nearly complete until dark matter, dark energy, and neutrino masses revealed gaps. There is no reason to think we have reached the end now. New experiments may reveal unexpected phenomena. New mathematics may unlock solutions currently out of reach. Breakthrough ideas often come from unexpected directions. The answer to quantum gravity might not come from string theory or loop quantum gravity, but from a completely different approach no one has thought of yet. What is certain is that our current understanding is incomplete. We do not know what gravity is at the quantum level. We do not know what spacetime is made of. We do not know why the universe has the laws it does, or whether those laws are unique or one choice among infinite possibilities. We do not know if singularities are real or artifacts of incomplete theories, or what happened at the Big Bang. These are not minor gaps. They are gaping holes in our picture of reality. Einstein's terrifying truth is not just that gravity is geometry. It is that geometry itself might be an illusion, a useful approximation that breaks down when examined too closely. The fabric of space-time is not a sturdy foundation. It is a fragile emergent structure, stable only because the underlying quantum information is organized in a particular way. Change that organization, and space-time changes. Destroy the entanglement, and space-time dissolves. We live in a universe held together by quantum correlations, by invisible threads of information connecting every particle to every other particle. Those threads can break, and when they break, reality breaks with them.